The fifth video in our Tools of Chemistry unit is on scientific notation. Scientific notation is probably a topic that you learned about in the past. You probably remember learning about it, maybe starting back in middle school or even late elementary. Here are our learning targets for this video. We have 3 learning targets. The first one, we should be able to express standard notation numbers in scientific notation, and vice versa, express numbers in scientific notation in standard notation, and then also perform basic arithmetic, meaning add, subtract, multiply, and divide with numbers in scientific notation. Here you can see your resources for this unit, your textbook pages. This first link here for videos is a playlist on Khan Academy for several different videos on scientific notation, including, I believe, all of the calculations that we're going to look at as well. Alright, so just some key ideas. First of all, what does scientific notation look like? Well, just a couple of examples here. The format here would be an example. Let's say I had 3.65 times 10 to the 8th. This would be an example of scientific notation. Or maybe it's 8.2 times 10 to the negative 4th. These would be examples of scientific notation. Every number in scientific notation has some number out front, that is some number between 1 and 9.9999 repeating, okay, could go on for longer, times 10 to some number x. We'll call x up there. Okay. You learned, when you first learned about scientific notation, you probably learned that it was for writing large and small numbers. Is probably what you learned. And that is still the case. We can still use scientific notation for this purpose. For example, this first number we wrote, 3.65 times 10 to the 8th, if you were to write that out in standard notation, that would be the same thing as 365 followed by 6 zeros. So it would look like this: 365 0 0 0 0 0 0. Okay, and the scientific notation makes it a little easier to write out. Doesn't take us as long. Don't have to worry about all those zeros. Likewise, this second number would be 0.00082. Now, if you're not sure how we got these, we'll see here in a little bit how we would do that. Okay. So the point is, we can still use them to write very large and very small numbers. However, when we get to chemistry, the use of scientific notation is a little more broad than just large and small numbers. Not that that's not good, because it is, but it's also for clearly showing significant figures. Because in scientific notation, if it's not a significant figure, the number disappears. So every digit we write in scientific notation is always significant. If it's not significant, it won't be there. So there is absolutely no ambiguity about what digits are or are not significant whenever we write in scientific notation. Just a couple of examples, and then we'll actually jump down and do the example problems down here. Suppose we had this number. We had the number 1200, and I wanted to write that to show how many sig figs there were and use scientific notation. Well, you might remember that whenever we write in scientific notation, what we're going to do is we're going to take the decimal point and we're going to move it until there's only one non-zero digit to the left of that decimal. So I moved it between the 1 and the 2. So this would be 1.2. I moved it 3 places to the left, so it's times 10 to the 3rd. And now if these 2 zeros here are not significant, they won't show up in my answer or my scientific notation when I write it. So this would be 2 sig figs here. If I wanted to write this number with 3 sig figs, so in other words, this first 0 here is significant, I would just write 1.20 times 10 to the 3rd. And that would be 3 sig figs. Likewise, if I wanted 4 sig figs, 1.200 times 10 to the 3rd. And that would be 4 sig figs. So we can see how whenever we write in scientific notation, every number that's not significant will disappear. We can also look at it the other way. Suppose I had this number, 0.0000570. Put a 0 on the end there. Well, I'm going to move my decimal until there's one non-zero to the left. So it's going to go here between the 5 and the 7. So I'll move it 1, 2, 3, 4, 5, 6 places to the left. That's going to give me 5.70, because as we know from our rules, this last 0 here is in fact significant. So I need that 0 there in my scientific notation. So 5.70 times 10 to the, now I forgot how many places I moved it, 1, 2, 3, 4, 5, 6. So times 10 to the negative 6. So if we go to the right, our exponent gets smaller. It's a negative exponent because our number is less than 1. So I have to multiply by a number less than 1 to make this work. Alright, let's jump down and look at the first set of example problems here. We're just asked to write each number in proper scientific notation. So what we'll end up doing here is all the non-zeros that are not significant are going to disappear. Alright, so this first number here, these 6 zeros, none of them are significant. So we're going to move the decimal over 1, 2, 3, 4, 5, 6, 7, 8 places. So this becomes 4.72. None of the zeros show up. Times 10 to the 8th. Alright, on B, we're going to move it to the right again until there's one non-zero to the left of the decimal. So in between the 7 and the 2. So this would be 7.2 times 10 to the, we moved it 5 spots, to the negative 5th. 7.2 times 10 to the negative 5th. Alright, C here. Again, these zeros at the end, those are placeholders, so those are not significant. I need to move my decimal here between the 9 and the 0 until there's one non-zero number to the left. So there's 6, 7, 8, 9 places, so this would be 9.072 times 10 to the 9th. Alright, on D here. This one's slightly different. It's actually kind of like the example that we did up above. This last 0, that is significant. So that needs to appear in our scientific notation. We'll move it 2 places to the right. That gives me 2.0 times 10 to the negative 2nd. Okay. Now, E and F are a little different. It already looks like it's in scientific notation. However, take a look at E here. You'll see that the decimal is not in the right spot. It should be a place where there's only one non-zero digit to the left. It should be here between the 1 and the 2. So we need to move it left 2 places. 1, 2. Now when we do that, our exponent needs to change. I know my number out front is going to be 1.2345. If we go to the left, our number out front got smaller. It went from 123.45 to 1.2345. So our exponent has to get bigger. So instead of 3, I need to make it 2 powers of 10 bigger. So that would be 5. So 1.2345 times 10 to the 5th. Same thing here on F. Our decimal is not in the right spot. We need to move it to the right 1 place. Again, we want one non-zero digit to the left. So this is going to be 2.90, because that 0 would be significant, times 10, and this is where it might get a little confusing. If I go to the decimal goes to the right, my number got bigger, so my exponent must get smaller. Well, my exponent's negative 7. My two options are negative 6 or negative 8. Negative 8 is smaller than negative 7. Remember, if the negative numbers, it's getting more negative, that would be getting smaller. So that would be times 10 to the negative 8th. Alright, one other example problem I want to look at here. It's at the top of the next page. We'll come back to this key ideas part here in just a second. Number 2 here. It says, write the number 300 in scientific notation with 1, 2, 3, and 4 significant figures. So we're actually going to write this thing 4 different times. Okay, so let's just write the number 300 here. Don't worry about getting the right number of sig figs yet. Let's just consider what this would be in scientific notation. Well, I would need to move the decimal 2 places to the left. and that would be 3 times 10 to the second. Now if I just write it like this, that would be showing that neither of those zeros are significant. So that would be 1 sig fig. So that kind of does the first one there, 1 sig fig. If I want to show two significant figures, then that would mean that first zero there is significant. So I would need a 0.0. So that would be 3.0 times 10 to the second. That would be 2 sig figs. That takes care of that one. And as you can probably guess, if I want a third sig fig, it would just be 3.00 times 10 to the second. That would be 3 sig figs. And then finally, my fourth sig, if I want 4 sig figs, 3.000 times 10 to the second with 4 sig figs. So as you've learned so far in our sig fig identification, sometimes those zeros can be tough, and we've talked about ways to deal with that, putting a decimal in a certain place or putting a line over a zero. My preferred method is just to put it in scientific notation, because there's absolutely no ambiguity that, okay, if you write it in scientific notation, then it is significant, always. Alright, going to go back to the key ideas sheet here, and we're going to talk about how we deal with these numbers in scientific notation whenever we have to use them in calculations. So I'm just going to separate this here a little bit. Alright, the first set of rules or type of calculation we'll look at is with adding and subtracting. Adding, subtracting. Same procedure whether we're adding or subtracting. Alright, the first thing we need to do, if we're adding or subtracting in scientific notation, we need to move the decimal so the exponents are equal. And we're going to kind of jump back and forth here between this page and the next page so we can see how these rules in action here. Okay, so if we look at the first example problem on number 3 here, on A, we have 2.6 times 10 to the 5th plus 3.7 times 10 to the 4th. Notice the exponents there are different. We need them to be the same. Now it does not matter which one you change, as long as you change one of them so it's equal to the other. I'm going to choose to change the one on the right here. It makes no difference. So I want this 4 to become a 5. Well, in order to do that, I need to move the decimal. If my exponent is going to get bigger, then my number out front has to get smaller. So my decimal has to go left. So I'm going to move it left 1 place, and the number on the right here would be 0.37 times 10 to the 5th. So I just moved the decimal left 1 place, and my exponent got 1 bigger. Okay, so that's the first step. Second step. We need to add or subtract, depending on what the operation is. Add or subtract the mantissas. You might be wondering, what the heck is a mantissa? Well, mantissas, those are just the numbers out front. Okay, you might call them coefficients, or they might have been referred to as coefficients when you first learned scientific notation. Usually, I don't think of them as coefficients just because they're not whole numbers usually. Not that a coefficient has to be a whole number. But these numbers out front here, these are the mantissas. So I'm going to add those together. I have 2.6 plus 0.37. Now when you do this, you need to follow your sig fig rules. Your calculator here is going to tell you 2.97. That's what it's going to tell you. However, notice that my first number here, the 2.6, only goes to the tens place. So I need to round to the tens place. I round for sig figs there. My next number is bigger than 5, so I need to round up. So the 2.9 will round to a 3.0. So I have 3.0. And then my last step, this is step number 3, is include exponent. And in parentheses I'm going to put check for proper scientific notation. In other words, is the decimal in the right spot? Okay, so going back to the example here, whenever we do the addition or subtraction, depending on what the operation is, we might get a number that doesn't put the decimal where it needs to, so you might need to move it. Now in this case I don't. All I need to do is add on my times 10 to the 5th, because that's the exponent that we changed it to. And there's our answer. Alright, so that's addition subtraction. These next few example problems here just are on addition subtraction, or at least the next couple here. So I'm just going to do those. You guys can follow along with me. Alright, example B. We have 9.78 times 10 to the negative 5th minus 2.3 times 10 to the negative 7th. Again, I need to get these to where they're the same, have the same exponent. This time I'm going to change my negative 5 to the negative 7. So if that's going to become negative 7, that's smaller. That would be a smaller exponent. I need to move my decimal right to make the number bigger. So I need to move it right 2 places. That would be 978 times 10 to the negative 7th. I've just moved the decimal to the right 2 places, and my exponent is now negative 7. Alright, so there's the first step. Now I need to subtract my mantisses. And this is subtraction, so don't add them together. So I'm going to take 978 minus 2.3. And your calculator, let me plug it in here, is going to tell you 975.7. But again, we need to follow our sig fig rules. My first value here only goes to the ones place. So I'm going to round this number to 976, because that's all I can keep. Okay, at this point, I can fill in my exponent, 976 times 10 to the negative 7th. Now here's the example of what we talked about earlier. This is not proper scientific notation. I need the decimal point to be here between the 9 and the 7. So I need to change this number a little bit. I need to move my decimal to the left 2 places. When I do that, that will make my exponent bigger by a factor of 2. So that would give me 9.76 times 10 to the negative 5th. Remember, negative numbers, it's getting bigger if it's getting less negative. So my answer here, 9.76 times 10 to the negative 5th. Alright, the next example, the last one with addition or subtraction. Notice we have addition here. And notice that the exponents are already the same. Okay, so I don't have to do anything as far as moving the decimal. I can start by simply adding the mantisses. 8.37 plus 4.2. And let's see, our calculator would tell us 12.57. Now for sig figs, the second measurement, second value, only goes to the tens place. So that's where I need to round. So rounding that, that would give me 12.6, because the next number is bigger than 5. So I now have 12.6 times 10 to the 12th. Same example as we just had. This is not in proper scientific notation. I'm going to move my decimal to the left 1 place. That's going to make my exponent 1 bigger. So that's going to be 1.26 times 10 to the 13th. Alright. You might be wondering, why do I need to move the decimal so that the exponents are the same? Well, recall that whenever you learn to add and subtract in elementary school, you were always told that you have to line the decimal up to do that addition or subtraction. This is the exact same thing. If you add these numbers, the mantisses, out front, and the exponents aren't the same, then that literally means the decimal is not lined up on those 2 numbers, and you're going to be adding values that make no sense. That's why you have to move the decimal so that the exponents that you're adding or subtracting, either case, are the same. Alright, so that's adding and subtracting. Let's take a look at multiplying and dividing. I'm going to go back to the key ideas sheet here. Okay, so we have our adding and subtracting rules, and we have our multiplying / dividing rules. And actually there's something slightly different for multiplying and dividing. They're not exactly the same. Alright, we'll approach this from the multiplying first. Okay, the first thing we're going to do is we are going to multiply or divide, and this is actually the same, just depending on the operation. We're going to multiply or divide the mantisses. So we don't have to worry about getting the exponents to be the same. They can be different in multiplying and dividing. Okay, so again, I'm going to go back to the first example on that. Alright, we have, this is example D, 2.4 times 10 to the 7th joules times 3.96 times 10 to the 4 seconds. First thing I'm going to do is I'm just going to multiply those mantisses. I have 2.4 times 3.96. So figure out what that is. My calculator tells me 9.504. Again, you need to follow your sig fig rules. Remember, multiplying, dividing, we're looking at number of sig figs. My first measurement only has 2 sig figs, the second one has 3, so my answer can only have 2. So that would be to the 10th place in this case, so this would round to 9.5. Okay, so there's the first step. Second step, and this really just applies to multiplying. There's a different second step for dividing. We'll put it on there when we get there. So whenever we multiply, we are going to add the exponents. And here is why. Recall from your math classes that if you have 2 exponents, say I have 10 to the 4th times 10 to the 3rd, so I have the same base 10, this would equal 10 to the 4 plus 3, or 10 to the 7th. Okay, so we just add the exponents. There's nothing different that's going on here that you've already done before. Here, I have 10 to the 7th times 10 to the 4th. So 10 to the 7th times 10 to the 4th would equal 10 to the 11th. I've added the exponents together. So now all I have to do is put these two things together. I have 9.5 times 10 to the 11th. Now here I have included units here. This would be joule seconds. And we're done. Do notice we are in proper scientific notation, so I don't need to change anything around. Alright, let's look at the next example here. It also is multiplication. So the first thing I'm going to do is multiply the mantisses together. I have 8.424 times 3.490. So if you plug that in your calculator, I get 29.39976. That's all well and good, except I only get 4 sig figs because both of those measurements are 4. So I'm going to count over 4 sig figs. 1, 2, 3, 4. That happens to be to the hundreds place. And rounding that for sig figs, the next digit is bigger than 5, so I'm going to round up. So this would be 29.40. That's what that would round to. Okay, so there's the first step. Now I need to add my exponents. I have 10 to the 8th times 10 to the negative 2nd. Don't forget adding and subtracting with a negative number. 8 plus a negative 2 would be 6, so that would be 10 to the 6th. So combining these things, I have 29.40 times 10 to the 6th. Notice, however, this is not proper scientific notation. I need to move the decimal one place to the left, and that will make my exponent 1 bigger. So this would be 2.940 times 10 to the 7th, and my units here would be meters times meters, which is meters squared. And there is our answer. Alright, so there's multiplying. The next 3 examples here are dividing. You might be thinking, well, the first part's probably the same. I should just divide the mantisses. You're right. So for F here, I'm going to take 4.5 divided by 1.5. Now your calculator is going to tell you 3. Except notice both of these have 2 sig figs. So I should have 2 sig figs in my answer. So this should be 3.0. Okay, so the first step is the same. Now obviously we're dividing, but the concept is exactly the same as multiplying. Now instead of adding our exponents, we're going to subtract. Because you learned back in math class, I'm going to go back to the key ideas sheet here. So this is step 2 if we divide. If we divide, step 2 would be to subtract the exponents. Because in math class you learned that if you're dividing, say I have 10 to the 8th divided by 10 to the 3rd, this would equal 10 to the 8 minus 3, which is 10 to the 5th. So I just need to subtract my exponents. Alright, so we'll go back here. So I have 10 to the 3rd divided by 10 to the second. Well, 3 minus 2, that's 1. So combining my values here, I have 3.0 times 10 to the first, and my units would be meters per second, because I have meters divided by seconds. And there we go. Alright, these next two examples, and these are the last two examples, these are both division, so we'll just see how those work. We have 9.7 times 10 to the third divided by 2.6 times 10 to the fifth. So just divide your mantisses. 9.7 divided by 2.6. That gives us 3.730. I only get 2 sig figs because both of those values are 2 sig figs. So that would give me 3.7. Now again, I'm going to subtract my exponents. 10 to the third divided by 10 to the fifth. 3 minus 5, that's a negative 2. 10 to the negative second. So I have 3.7 times 10 to the negative second. My units, grams per centimeters cubed. And there we go. Alright, last example with the division. 2.2 times 10 to the fourth. Capital C is coulombs. It's a unit of electric charge, is what that is. Divided by 3.3 times 10 to the negative second. So I take 2.2 divided by 3.3. Your calculator is going to tell you 0.66666 repeating on forever. But as we know, our numbers can't actually go on forever because there is no exact measurement. Both of those are 2 sig figs. So to the second sig fig, that would be 0.67 is what that would be. Now I need to subtract my exponents. I have 10 to the fourth divided by 10 to the negative second. Don't forget, subtracting a negative value would be like adding. So 4 minus a negative 2, that would be like 4 plus 2. That would be 10 to the sixth. So I have 0.67 times 10 to the sixth. Notice, however, I need to move my decimal over one place to the right. If the decimal goes right, my exponent has to get smaller, so that would become a 5. So this is 6.7 times 10 to the fifth, and my units here would be coulombs per meter. And there are the examples. Alright, the last page, page 3, are some practice problems. So I would stop the video now and try these on your own. Alright, first practice problem, we're asked to write these in scientific notation. The first one would be 3.75 times 10 to the fifth. Those zeros there are not significant, so they would disappear. The next one, we would have 2.500. The last two zeros are significant, so they need to stay there. Times 10 to the negative third. I need to move the decimal 3 spots to the right. C, actually, I don't get to lose any of the zeros. They're all significant. So 4.0000 times 10 to the second. Very clear way to show 400 with 5 significant figures. And the last one here, this would be improper scientific notation. I need to move the decimal to the right 2 places. So that will make it 3.4. And then since I move my decimal to the right, the exponent should get smaller. So that would be times 10 to the negative sixth. Remember, more negative would be the smaller value there. Alright, the last part of the practice, we just have some of the calculations. Alright, the first practice, we have addition. So remember, our exponents need to be the same. I'm going to change the first one here from 10 to the 18th to 10 to the 19th. So to make the exponent bigger, my decimal needs to go left. So if my decimal goes left one place, that would make this 0.275 times 10 to the 19th. Okay, so now I need to add the mantisses. 0.275 plus 3.48. 0.275 plus 3.48. That gives me 3.755. Don't forget to round for sig figs. Here I only have a sig fig to the hundredths place.